Hello everyone. Today we are presenting as Group 9 our image similarity project that we will be comparing DinoV2 and SwAV algorithm. So let's go to the next slide now. So for the DinoV2, let's talk a little bit about it. So DINO stands for distillation with no labels. And this algorithm and this machine learning model was proposed by Meta AI, further known by Facebook AI research. And it is a massive improvement of the original DINO algorithm. So what do we have to learn about this? This is a self-supervised model. And it uses vision transformer architecture, also known as ViTs. And also, in order to pre-train it, the researchers used filtered data set of more than 100 million diverse and high quality images. And this is very important for the pre-training phase. And also, this algorithm breaks images into smaller patches for comparison purposes. And this machine learning model does not require any labels. So it's something we have to highlight here. So now let's switch to the next slide about the interpretation and the information about DinoV2 model. So what about the architecture? So here is some information about the architecture. So as you can see about the embed dimension, the head blocks, and also it has a feed-forward network layer called multi-layer perceptron, as you can see. Also, during the pre-training phase, the researcher used the optimizer called ADEMW. And for the hyperparameters from the paper review, we saw that there was 5 hyperparameters, such as the learning rate, as you see, the initial layer scale value, the learning rate warm-up, the weight decay, and also for the last, the teacher momentum. And also, according to the paper that we reviewed together, the number of epochs used in order to train the model is more than 600,000, as you can see, and they used the dataset ImageNet dataset batch size 2048 for the pre-training process.
So this is basically the information of the pre-trained model we have also used in our implementation. Next up, on the next slide, please. So next I'm going to be explaining SwAV, which is swapping assignment between views. This is the second technique that we have used for image similarity problem. Again, this is a method that was proposed by Facebook AI research in 2020 paper. And this is a self-supervised model. What that means is it does not require labels. So on your right, you can see some architecture. So what that means is it takes an image and it takes different views of it. When I say view, it means like you crop the image in different parts and you will find different parts of the image. So those are known as views. If we go on the next slide, it explains how it works. So you for an image, we have multiple views, and for each view, we convert it to embeddings or features. And then for each features, we make the prediction like uh, uh, so so basically self-supervised learning is like clustering, right? So you have got prototype just means how many clusters that there are there. So prototype assignment means like let's say if I have 3,000 prototypes, what is the probability that my feature belongs to prototype 1 or 2 or 3 and so on. So it's just a probability vector of the prototype. So that's what SwAV does. And then the way the loss is calculated is it takes feature one and predicts like it compares predicts prototype for assignment 2, and then it compares the true value of view 2 and the predicted assignment of view 1 based on feature 2, And that's how it swaps the assignments to calculate the loss. Next slide, please. Why SWAV? So it's different than the contrastive learning algorithms like SimCLR because it avoids using huge batches, and it trains fast and efficiently. And on the next slide, we'll see the architecture of SWAV that we are using for our pre-trained model. So we have imported a ResNet 50 model of SWAV, and then these are the hyperparameters and the number of epochs it has been trained on, and all these info is given in the paper as well as the GitHub repo from which we have taken this model. Over to you, Nimisha.
So the steps we followed are first we got the tiny ImageNet data, and we created pairs of that data for our evaluation, which we then fed into the pre-trained models. These then extracted the features, and we also did a combination of both the models for an ensemble model. And for all three of them, we compare and evaluate the results. So as a part of the data preparation, we just got the train test and validation split for Tiny ImageNet. And for the pairing, we paired images into the same class and different classes. And here you can see how many of those we have. And then we passed it off to DinoV2 and SwAV for the feature extraction. And as you can see, they extracted 77 features. And then they did the comparisons for the image pairs. And we had 12 million image pairs from the Tiny ImageNet test split, which when compared, you can see the results here that we got pretty high accuracy, but our precision was pretty low, which will be covered by Akansha.
Yeah, so in this slide, we will be discussing about SWAV similarity distribution. And here we can see that we have two histograms. And the left one shows blue bars, which are the same class pairs, and the right one with the orange bars, shows the different class pairs. The threshold 0.810 is SWAV's optimal cutoff to classify pairs as similar or dissimilar. And so we can see that there is a heavy overlap between the two distributions. beanswap often assigns similar scores to unrelated images, and which results in ambiguity, as same class pairs they peak around 0.8 to 1, but many score lower, while different class pairs they cluster near 0.6 to 0.8, and so this results in frequent misclassification. So we will be comparing it with DinoV2's histogram. Here we can see that same class pairs, they concentrate here, and different class pairs they cluster near this area. And the threshold 0.370, it cleanly divides the two groups. So this minimal overlap, it shows that DinoV2's embeddings they clearly discriminate between classes, and most same class pairs they score above 0.6, while different class pairs rarely exceed 0.4, and this aligns with DinoV2's near perfect accuracy, which is 99.5%, and area under the curve, which is 0.936. Its vision transformer architecture, it captures semantic differences more effectively than SwAV's ResNet based approach. In this slide, we will be seeing that how ROC curves they quantify this difference. DinoV2's orange curve, it approaches the top left corner that because it has high AUC, and it indicates excellent true positive rates with few false positives. And the SwAV, that is the blue curve, it stays closer to the diagonal, reflecting its struggle to distinguish classes. So we can say that DinoV2 superiority, it stems from its self-supervised training on diverse samples, while SwAV's prototype-based clustering, it lacks granularity for fine-grained similarity tasks. So in this slide, we'll be discussing that how we use SwAV's prototypes for coarse clustering and DinoV2's embeddings for fine-grained similarity. We also trained a classifier to weight predictions from both models dynamically called the meta classifier. And our goal was to mitigate SwAV's ambiguity while preserving DinoV2's precision. Here we can see that SwAV, it is inconsistent. It excels in classes with distinct prototypes and but fails on fine-grained categories. And DinoV2s also, we can see that how it has these best performing and these worst performing classes. In this, we will be discussing about advanced ensemble method, and we can see its accuracy is 99.57%, which is higher than DinoV2's, suggesting the ensemble corrects a few edge cases. Precision is 71.97%, which is a significant drop from DinoV2's, indicating more false positives. Recall, it is much lower than DinoV2, meaning the ensemble misses more true positives. F1 score, it reflects the trade-off between precision and recall. So AUC, it is 0.9386, which is slightly better than DinoV2, which shows a marginal improvement in overall classification ability. So the ensemble, it achieves near perfect accuracy, but at a cost. It's overly conservative. This suggests that the meta classifier, it prioritizes avoiding false positives, but misses true matches more often. So here we will be summarizing our final results, which show that accuracy, it exceeds 99%, demonstrating near perfect classification. And precision, we can see that this precision, it reflects very few false positives. This means that the model predicts a pair is similar and it is likely correct. This recall, it is lower, which indicates that the model misses 60% of the true matches. And this F1 scores, it balances precision and recall. And the higher value suggests the ensemble, it mitigates extremes in certain configurations. And this AUC has high values, which shows that robust separability of the classes. So these were the references that we used. Thank you so much.